Exactly.
I'm listening. Come again.
Exactly. Lenses. I would say a lens is a transparent optical device that reflects light from an image.
That's come again. A transparent optical device that
reflects light from an image.
from an image. I'm listening to your key stuffs. Okay, so let's polish. What you said isn't wrong, but there are some misconceptions which we need to clear. Somebody to also give me another view of what lenses are. Michelle.
A lens is any piece of transparent substance bounded by two spherical surfaces, or one is a plane substance and the other is a spherical surface.
So bounded by two or one spherical surfaces. Okay. Yeah, last one on lenses. Yeah, Yasmin. Last one on lenses. Then we move on. Yasmin.
The lenses are transparent materials that refract light rays to form an image.
That
refracts
okay.
Light rays to form an image.
So all the contributions excellent. So listen, just as you said, a lens is a transparent refracting medium. A lens is a transparent refracting medium bounded either by two or one. I hope you are writing. A lens is a transparent refracting medium bounded either by two or one spherical surfaces. Okay, so what it therefore means is that Ablina, lenses refract, they do not reflect. Mirrors reflect, but lenses refract. Lenses and prisms. Lenses are just like prisms. They bend, refract light. Okay, so do I take it again?
Yes, sir.
Elikam, your hand is up. What's your secret?
Sir, please come again.
Okay, so I said lenses or a lens is a transparent refracting medium. A transparent refracting medium bounded, just as Ablina, Michelle, and Yasmin, bounded either by two or one, spherical surfaces. So we can have either two spherical refracting surfaces or one. Okay, and lenses are they bend or deviate light. All right, so let's look at the types of lenses. And then this time I need the gentleman to also contribute. Types of lenses. Yes, Ella, you are not a gentleman, no.
I'll be a man for now.
Okay, let the men exhaust their view and I come to you, okay? So Ernest.
Hey.
Types of lenses.
Sir, please, should I say all of them or I should only see how many there are?
Just give me one example so others can also.
Sir, one is the concave lens.
So Ernest is talking about concave lens. So concave lens or
Divergent.
or diverging lens. We'll later probe why. So we have concave lens or diverging lens. Gideon.
It is convex lens.
Convex. Convex or
The convex
Converging.
or converging.
converging. Okay. So can you describe what a concave lens looks like? And then no, we are not done. Three. Do I go to the ladies, gentlemen?
No, sir.
Okay, Ernest.
Sir, sir, I think the two are the only ones we have.
No.
So mine is up.
Sir, can we say photochromic lenses or?
No. Okay, let's hear from Echo. Echo is ready to share something with us.
Sir, please, plano concave and
We also have plano concave
and plano convex.
and plano convex. And then lastly, Gideon.
So we have bioconcave and bioconvex.
What?
So we have bioconcave and bioconvex.
I get what you are saying. Then we have concave and convex meniscus. These are all names that are given based on the shape of the refracting surface. Meniscus. So we have concave meniscus and convex meniscus. So these are the. Now, you made mention of concave lens or divergent lens. You see, that Gideon, what we have, the concave lens, the convex lens, we have some of them with, you see, when we're defining lenses, you were talking about one with either two or one refracting spherical surface. Okay, those lenses with two spherical refracting surfaces are known as the so we have biconvex and biconcave. The bi implies that we have two spherical surfaces. Okay, the planos have a single refracting surface. Okay, the meniscus have a refracting surface, okay, which is shaped like the meniscus of water and mercury, respectively. But let's understand the shape. How would you describe a biconvex lens? How would somebody describe it? Ella, how would you describe or explain what a biconvex lens is? Ella, you are a man for now. Can you describe how a biconvex lens looks like?
There is a lens with two convex surfaces that is thicker at the center of each edge, at the center of the edges.
Come again.
It's a lens that's that has two convex surfaces that is thicker at the center of each edge. Yes.
Okay. So the biconvex lenses, as I said, the bi means that we have two refracting spherical surfaces. The convex lenses are thicker in the middle and then thinner at the edges. Or the refracting surfaces curve outwardly. Okay, so this is how the biconvex lens looks like. So it is thicker in the middle, but at the edges, it is thinner. Or the refracting surface or surfaces curve outwardly. Class, are we okay? Then the plano. The plano means that we have only one refracting surface. Here, one side curves outwardly and the other side is flat. So all the plano has one refracting surface. Okay, so this is plano convex, then biconvex. Then the convex meniscus. With the convex meniscus, yes, we have the refracting surface curving out, but the other part, it's shaped like the meniscus of water. So this is the refracting surface, but the other side isn't flat, but it's shaped like the meniscus of water. How would somebody describe concave lens? How would somebody describe concave lens? Yes. Anybody to help us here? Yes, Gideon. Okay, so let's Saki come in. Saki.
Is the concave
Let's not
lens
waste time.
is the concave lens is thinner in the middle than the edges. It also
So
spread light rays apart.
So what you have to say is that it is thinner in the middle and thicker at the edges. This one is thicker in the middle and thinner at the edges. Okay, so the biconcave looks like this. Good. So we have, these are the refracting surfaces. Bi. In the middle is thinner, at the edges it's thicker there. Then plano concave. Yes, the planos have a single refracting surface. The other side is just flat. This is plano concave. Then the meniscus. So this is the refracting surface. The other side is shaped as the meniscus of mercury. Okay, so these are the three main types of lenses. The biconcave, biconvex. They are named, you see, when you look at for mirrors. Class, what kind of mirror is this? Look at what I've shaded. What kind of mirror is this?
Concave.
Concave. Why? Because the reflecting surface curves inwardly. So this one, because the refracting surface curves inwardly, the reason why this is also concave lens. Okay, whether bi or plano. And then this is convex mirror, isn't it? The reflecting surface curves outwardly. And so this is also because the refracting surface curves outwardly, the reason for which this is also convex. So the name is actually born from the shape. You can use this to get there easily. Please, is there any question on this? We are moving on to the uses of the mirrors, the lenses. So let's look at Frank. Frank, speak up. Frank, speak up.
Please, if you ask the question to state the types of lenses, if you're writing concave lens or divergent and concave and convex, you write bioconvex and bioconcave.
So you can be specific. Biconvex, biconcave, plano convex, plano concave, and then convex meniscus, and then the concave meniscus. But generally, you see, these are we have convex and concave because it depends on the shape. But if the question asks you to list, when you list this, you are not wrong. Okay. All right. So uses. What do we use lenses generally for? Uses of lenses. Here we are combining all of them, both concave, convex, whether it's plano or yes. What are the uses? Share with me some of the things you saw. Augustine, start for us. Hey, Daisy, you've not been talking. Frempoma, Anita, you also Anna. Come again.
Step is Michelle too.
Michelle has been contributing. Okay, Elikem. 1.
Binoculars.
Lenses are used in what? Binoculars for what purpose? What do they do in the binoculars?
So they help make objects afar seem closer.
Okay, so they are used in binocular for clearer vision. Let's make it general. In binoculars, cameras, they are also used in cameras. Telescopes, microscopes, etc. for clearer viewing. Then, yes, Augustine, I have gotten you. So the magnifying glass, which is a simple microscope, the magnifying glass, let's include that. It is also used in magnifying glass, this is what we call as the hand lens. The hand lens, obviously for clearer viewing. So when you use a camera, let's zoom the person. Let's adjust the camera so that the object okay, will go far, will come nearer. All these adjustments are done using lenses. Okay, a distance object, telescope, can be brought to viewing using, so the telescope is basically an embodiment of these lenses, prisms, lenses, and all that. Okay, so that's it. 2 uses of lenses. Afari.
With laser systems.
As what?
Laser systems. It's used in laser systems.
It's also used in laser systems to concentrate light. Do you know we can even use, yes, when we're in school, we're using the hand lens to set fire, okay, in papers. Okay, so it can be used to concentrate the heat energy to ignite, and that is what is used in laser systems. Okay, Elikem.
It is used in projectors.
It is also used in projectors, yes. Used in projectors. And do not forget your glasses, your glasses. Your glasses. It is also used in glasses to correct eye defects of the eye. Martin again.
It's used in virtual reality headsets.
Yes, virtual reality. Yes, all these. Yes, in a cinema, projectors, this virtual reality are also used, and so on and so forth. Okay, then it is also used in as eye contact lens. You see, when you have a problem with your eye, especially the lens of the eye, okay, surgical operation can be done, and then the damaged lens, natural lens of the eye, can be replaced using artificial lens. Okay, so it can also be used to replace the natural lens of the eye. Then lenses are also, especially the convex and then concave meniscus, can be also used as contact lens for the eye. Contact lens. So especially the ladies, they can go to see these people so that these thin lenses can be placed on their eye to change the color of the eye and all that. These are those lenses that are shaped in the form of meniscus just to fit the size of the eye. Saki.
Please have written projectile instead of projector.
Oh, okay. Thank you. So projectors. Please, have you exhausted the uses? So use as contact lens, your optical glasses for correcting eye defect and so on. Genius, Saki.
That is to speak.
All right. Morris.
So please, how about projectors?
What, projectors?
Yes. Is it using projector?
Yeah, it's been mentioned.
Okay.
Okay. It's been mentioned. Frank.
Sir, please, lenses used in goggles to protect the eyes from like water?
Goggles are not curvy. Goggles are just transparent. It can be glass, it can be plastic. But don't forget, lenses are bounded by spherical surfaces. So lenses must be curvy. So the glasses you use whenever you visit the optician, okay, they are all curvy, but goggles are not curvy. Frank, are you okay?
Yes, sir.
Okay, Martin.
Please, optical sensors.
Optical sensors, and they are also used in the laboratory. Yes, we also use lenses in the laboratory for experimental purposes, okay, which you will be experiencing. The ladies are not talking. Saki, is your hand up?
Yes, sir.
Sir,
please, can you say security cameras?
Security cameras zoom. They can zoom. Yes. So long as we have this zooming thing, yes, there will certainly be lenses. And don't forget, you see, cameras generally have lenses within. So we can also say security camera, CCTV. All right. So we can have a lot of Ella.
Sir.
Ella, the last contribution from Ella or Frank. Ella, are you ready?
Yes.
Okay.
Please, what of torchlights?
Yes, torchlight. You see, torchlight, the reflectors are not lenses. So torchlight, the reflectors are mirrors, curved mirrors. Well, lenses must refract, bend. So it means that light must actually pass through them. Are you okay?
Yes, please.
All right. So I think this will do for uses of lenses. Let's look at the parts. Lenses have aperture, just as mirrors also have. So this is, okay, before we move to the parts, why do we call convex lenses converging lenses as well? A converging lens. This is a convex lens. Convex lens. Why do we call this? Anita, let me call Anita. Anita, why do we call convex lens a converging lens?
So please, because the reflected rays meet at a point. The refracted rays, sorry.
Come again.
The refracted rays meet at a point.
The refracted rays meet at a point. Okay, more views. More views. Anita is saying the refracted rays meet at a point. What is Saki saying? Then I come to Ella.
Sir, please, it causes rays to meet at one common point.
It causes rays to meet at one common point. Okay, Ella.
So since the convex mirror is thicker at the middle side, it should I say it attracts the rays of light, the parallel rays of light to focus at a focal point, which then like it comes together at the focal point. Yes, that's the reason why.
Okay, all right. I think the key point, okay, have been mentioned. So just as you are saying, when you incident parallel rays to the lens, not just any direction, but the rays must be parallaxial rays. This lens, convex lenses have the tendency to deviate or refract the light and bring the refracted rays to a common point. Bring all the refracted rays to a common point. So this would be here. This would also be here. This will also be here. And this is the reason why we can use this as to set fire, to set up fire in papers. Because when you direct the hand lens, the magnifying glass today, it can be able to converge, bring together all the sun rays coming to it in that parallel manner. Okay, so this has the ability to converge parallel rays. So this is the reason why we call convex lenses converging lenses as well. Okay, then diverging concave lenses are also known as diverging. This is because it can be able to disperse or spread out refracted rays. So when you incident rays that are parallel to it, let me use freehand to save time. This one has the ability to diverge the refracted rays. Okay, or they spread out after refraction. Frank.
Sir, please, I learned that in the lenses there's a line that divides it into two. It's called the optical axis. That's where the ray like refracts in the prism. But when you drew it, it's refracted like at the surface of one of the sides of the lens.
The bending actually occurs at the boundary between air and then the the boundary between air and then the glass. Within the prism, it will not bend. Okay, then from glass to air, how it bends will be the same as how it entered. Okay, yes, I'll draw the line through. When we come to ray diagram, you understand. But the bending actually occurs within at the boundary, just as we saw in refraction. All right. So these are concave, converging, and then diverging lenses. Then let's look at parts of the optical lens. Parts, just as parts of the thin lens. Parts. Now, this is the lens. Okay, if this is, let's draw a mirror. The length of the mirror AB is the aperture. We have the same thing in lenses as well. Okay, that vertical height is the aperture. The center of the mirror is known as the, what name do we give to the center of the mirror?
Principal.
What name do we give to the center of the mirror? Hey, you've soon forgotten.
Principal axis.
No. No.
The pole.
The pole.
Yes, sir.
The pole, which you cannot score, but is the pole. The center of the lens is this time known as the optical center. Optical center. This is the pole. Here is the pole. But in lenses, the center is the optical center. A line through the optical center also through the center of the whole sphere is known as a line passing. Axis. That's the principal axis. The center of the whole sphere, which is also part of the mirror, is known as the center of curvature. We also have the same thing, a line through the optical center, okay, also through the center of the whole lens, the optical center C, right? Then this distance, I'm using, because we've done mirrors, I'm using mirrors to also draw your attention to this. This distance from the pole to the center of curvature is known as this distance from the pole to the center of curvature is known as
focal length.
No. Radius of curvature. Radius of curvature. Yes, the same distance is known as the radius of curvature. Are we okay? Then, you see, for mirrors, because they reflect, we have a point where rays that are parallel are reflected to a common point. So a point on the principal axis where parallel rays are converged. This distance from the pole to that point, we call this point a point on the principal axis where rays that are parallel are converged after reflection to be the principal focus or the focal point. Now, for lenses, if you incident parallel rays, they will be refracted and after refraction converge at a common point. This point where parallel rays actually converge after refraction is known as the focal point or the principal focus. So we have the same thing here. The only difference is that lenses refract or bend light. Okay, so when you incident two or more parallel rays, they will all converge at the point. We've talked about why they are converging. And that point where the refracted rays actually converge is known as the principal focus or the focal point. Now, note that for biconvex, because we have two refracting surfaces, it means we have two principal foci. One here, so we have F1 here, and we have the same point also at the other end. And these points are known as conjugate foci. Conjugate foci. This is because, you see, we have two refracting surfaces. So light can come from left to right and will converge at the right. Light can also converge from right to left and will converge at the left. So we have two different principal foci at both ends. Whereas for mirrors, we have only one. Please, if you have any question, quickly ask. Equally, for biconvex, we also have two center of curvature. We also have two center of curvature. The center of curvature for lenses is not C, but it is represented as 2F. So if this is F, 2F. The other end, we also have the same thing, 2F. for bi, meaning if it is plano, there will be one. If it is plano, example, if we have plano convex, there's the principal axis. When you incident light here, it will refract, converge here. When you incident light here, it must refract and converge here. So plano will give us one principal focus. Class, are we okay? Class, are we okay?
Yes, please. Yes,
okay.
Please.
Please note that rays are denoted with arrows. So incident and refracted rays. You don't overlook that. Okay, let me take attendance and then be with you. Whilst I take attendance, Frank, Saki, and Co, if you have any question, you can ask. Elikem, if you have any question, and Anita, Ella, Pointiwa, if you have any question, quickly ask. And so understanding of mirrors would actually help us so much here.
Recording in progress.
Okay, so I think we can continue. All right. Now, note that still R for lenses, R is equal to the radius of curvature, which is the distance from the optical center C to 2F. R is equal to 2F, meaning that this is the focal length. F, another F, okay? And this distance from the optical center to the center of curvature 2F is what we are calling as R. Let's look at how concave also deals with parallel incident light. In ray diagram formation, instead of writing convex mirror lens as this, there is a short rotation. I can draw a vertical line and then curve the edges simply, and in ray diagram is the same as convex lens. If it is concave lens, I can also draw it simply by drawing a vertical line, then shaping this edge shaping this edge, and it qualifies for concave lens. But this is only for when you are doing ray diagram instead of doing this. So if we have a concave lens and you incident parallel beam of light, how will it bend? So this is a principal axis passing through the optical center C. If I incident parallel ray here, this ray would diverge after refraction. It will diverge after refraction like this. Okay. Note that when a ray hits the optical center, it goes undeviated. When a ray of light hits the optical center, it goes undeviated. Just as in mirrors, when a ray hits the mirror at an angle of 90, okay, it is reflected back along the same line. Please, are we there? So let's quickly look at formation of images. Formation of images in lenses. How does concave lens form an image? Here, let me use a straight line. So a convex lens, so we have a vertical line, and then I will only shape the edges. So Frank, this is done in ray diagrams. Ray diagram, not when you are drawing convex lens or concave, okay? So if this is the center, the optical center, let's draw the principal axis. Since this is bi, I must have the two different principal foci. So F1 here. Then the same measurement from the optical center. I'm just estimating, but when you are doing this, please take real measurement. F2. So we have the primary principal focus and then secondary principal focus. Then R, which is 2F, is equal to 2 times F. So the same measure.
Yes.
Angie, mute yourself. So 2F here, and then another 2F here. Okay, so just as we saw in mirrors, you are also free to decide where the object must be placed. Okay, but there are rules for doing this. The same rules we saw in mirrors. The first rule is that a ray of light parallel to the principal axis, when the ray from the object is such that it is traveling parallel to the principal axis, after refraction, it must refract and pass through the principal focus. So the refracted ray must pass through the principal focus. Rule 1. So incident, refracted. Okay. Then the second rule is that So let me label them. Rule 1. Rule 2, let me change color. A ray of light coming from the object through the principal focus, so long as the ray is passing through the principal focus. After refraction, the refracted ray must go parallel to the principal axis. The refracted ray must go parallel to the So let's draw an incident ray, then refracted ray. This is rule 2. Alikem.
Sir, please add the network now, so I don't understand.
We are looking at rules for formation of images in lenses. Rules, let me write it up here. Rules for the formation of images in here convex lens. We'll look at it for concave. So rule 1 says that when the ray is parallel to the principal axis, after refraction, the refracted ray must refract and pass through the second principal focus. Okay, so this is rule 1, and this is rule 2. Rule 2. Then the third rule is that a ray of light passing through the optical center goes undeviated. Gideon. Oh, this is what I've drawn on the diagram. We see the rule 1 drawn in pink. Okay, the ray is such that it is traveling parallel to the principal axis. This is the principal axis. And the rule is saying if the ray is parallel to the principal axis, after refraction, it must deviate or refract and pass through the second principal focus. Angie.
Yes, sir. So I was asking if the rules for image formation in the lens is the same as that in the mirror.
Almost. You see, the only difference is that it is almost the same, but the only difference is that lenses refract light, whereas mirrors will reflect. So if this had been in mirror, concave mirror, let me use this for an illustration quickly, and it will help us understand this one. So it's almost the same. The first rule, a ray of light, let me indicate the principal focus. So in mirrors, we'll have only one principal focus. So when the ray is parallel to the principal axis, Frank, I'm coming. Let me answer Angie's question and I'll get back to you. When the ray is parallel to the principal axis, after reflection, it will reflect and pass through the focal point or the principal focus. So in mirrors, this is rule 1. In lenses, The same rule, a ray parallel to the principal focus, because light will pass through as a transparent spherical material. So light will pass through, and after refraction, it must pass through the second principal focus. So Angie, it's almost the same thing, but you must understand that this would refract and mirrors will reflect. That is all. Frank.
So because mirrors reflect and their lenses refract, so concave in mirrors is opposite to concave in lenses.
See, that is why I use mirrors to explain to you. This is concave mirror. And concave mirror, the reflecting surface curves inwardly. Then we have, supposing we have plano. One side is flat, the other is straight. Okay, look at this refracting surface. Does it curve outwardly or inwardly? Frank, look at this. Does it curve inwardly or outwardly? Hello, Frank.
Inwardly.
This curves outwardly. The refracting surface curves outwardly. So you see, that's what, so it's like the opposite thing you are talking about. In mirrors, this is concave mirror, but in lenses, this is convex. Are you okay? So it's similar to the opposite thing you are talking about, but you can still use the drawing to make the meaning clearer for yourself. All right, so the second law is saying that if a ray is passing through the principal focus, and let's do that for mirrors. A ray of light from the object passing through the principal focus, after reflection, the reflected ray must be parallel to the principal axis. In lenses, all that we are saying is that if the ray is passing through the first principal focus, after refraction, it must refract in such a way that the refracted ray is parallel to the principal axis. They say almost the same thing. Please, class, are you okay?
Yes, sir.
Then the third rule. I told you that when a ray in mirrors, when a ray hits the pole, a ray of light passing through the pole reflects back along the same path, would reflect back along the same path. In lenses, a ray of light from wherever passing through the optical center would go undeviated. Let me change the color. Here, so long as the ray passes through the optical center, it will never be deviated. It will just go straight. These are the three rules we'll be using for formation of images in lenses. So rule 3. Angie.
So Angie, do you mean like it will not be refracted as the light will not bend?
It will not bend. Parallel, it will bend and pass through F2. Okay, if it is passing through F, it will bend and then be parallel to the principal axis. But when it's passes through the optical center, it will not deviate, it will not bend. Are you okay?
Yes.
Note that, Frank.
Sir, I'm confused. The line that is in the middle of F1 and F2, is it the surface of the lens?
The line that is in the, Frank, I was saying that instead of drawing convex lens like this, a short form notation is that draw a vertical line and curve the edges. Curve the edges. This would also stand for biconvex. So that vertical line is the optical device convex lens. Frank, are you okay?
Yes.
You are not okay. Ask.
Sir, it like the line, if like to me it feels like it's the middle, like the whole from 2F on the left to the right is the whole. I thought it was like the whole like lens.
This is the lens, which this is the whole lens. But I just didn't want to write it like this. So what I have there is just like a symbolic thing to represent the lens, Frank.
So say like that you draw a line like to divide the lens. So that means the line, like the light ray is refracting inside the lens, isn't it?
What I'm saying is that refraction occurs at the boundary between air and the lens. In between, within the lens, okay, it will not bend again because it's just traveling through the same medium. So the deviation actually occurs here, would occur here, would occur here. So in actual sense, it will bend here and pass through F2. That's what I'm saying. But if you use that vertical line, you cannot see that. Are you okay?
Yes, sir.
All right. Please, is there any other question? Because we are going to place objects at different positions and then put, okay, we have to discuss how convex would also, concave would also behave. So let's do it for my good brother concave. So Frank, I'm not drawing the whole concave biconcave lens, but just a symbolic thing. Okay. So if this is the optical center, Daisy, are you there? Daisy, these days
Yes,
you don't talk. Oh.
Sorry, I'm very sorry. I'll start talking more often.
Exactly. Augustine too. So if this is convex, now note that for convex, the two principal foci are all virtual. So F1 is virtual, F2 is also virtual. Then the center of curvature 2F is also virtual, but for convex, these are real positions. So when you incident parallel beam to this, if a ray is traveling parallel to this, what will happen is that it would diverge it. but the diverted ray must appear to be diverted from this. So the diverted ray would go in this direction. Okay. In actual sense, this wouldn't show. Another parallel ray will be diverted, but the diverted ray always appears to be diverted from this point. So it will go straight like this. So this is a refracted ray. Refracted ray. This is the incident ray. This is the incident ray. And this is the reason why the principal focus of concave lens is virtual. Because this point where diverted ray appears to be diverted from are actually not real points, but they are virtual positions. Please, are we okay?
No, sir.
So this is how rule 1 is applied to concave lens. Then rule 2. To show that this is concave, I must do this. What is rule 2? Rule 2 is saying that if the ray is passing through this F after refraction, it must be parallel to. So this is my virtual principal focus. Please give me a minute. I'm coming in. I need to pick this urgent call from school. The second rule is also saying that if the ray seems to be passing through F, if the ray seems to be passing through F, so let me use two rays, one up and one down. For a better understanding, I need to break this. Okay. Let me draw a line. So the ray seems to be passing through F2. So here, Then I continue. What it means is that the ray is coming from here, but it appears to be passing through F2. This ray is also coming from down here. Appears to be passing through this. If this is the situation, the ray seems to be passing through F2, then after refraction, the refracted ray must be parallel to the principal axis. The refracted ray must be parallel to the principal axis. So in this case, this will be the refracted. Okay, this is the second rule. The second rule is just the opposite of the first one. Okay, a ray parallel to it after refraction must appear to be refracted from or diverted from F. A ray which appears to be passing through F after refraction must be parallel to the principal axis. Then the third one is the same. Once the ray passes through the optical center, it will go undeviated, just as the first one. So the third rule is the same for both convex and then concave. Once the ray hits the optical center, it would go undeviated from wherever it is coming from. So these are the three rules we'll be using for our ray image formation in lenses. Please, are we okay? Usually, because these are virtual points, F, virtual points for concave lenses, we use broken line to represent it. We use broken line to represent it, but I don't have that feature here. Saki.
Sir, please, can you go over the first one again?
For concave lenses. So the first one, yeah, this is it. This is the first one. A ray of light parallel to the principal axis, okay, after refraction, you know, concave will diverge or divert refracted rays. But the diverted ray appears to be diverted from the principal focus. That's why I said these are virtual points. These are virtual points. So when the ray is parallel to the principal axis after refraction, yes, it will be diverted, but the diverted ray appears to be diverted from. So when you are drawing the diverted ray, you must link it to F, else you get it wrong. Okay, and the second one is just the opposite of this. If it is parallel and it appears to be diverted from F, then once it is passing through F after refraction, it must be parallel to the principal axis. So this is actually the reverse of the second one or of the first one. Class, are we okay?
Yes.
Okay. Then let's give ourselves a real question. Vary object position and use ray diagram to determine the nature of the image form. So I'm starting it for convex. I'm coming in. I just want to update attendance. All right, so I'm going to do one or two because we've done mirrors. I wouldn't waste time on this. You do. So there's the optical center C. Please take measurement of the focal length. So this is F. This is the same distance. You should take measurement. I am estimating, so 2F. Then this is by, so we have the same measurement at the other end. F and (2F). Now, place the object anywhere, and let's place our object behind 2F. Just as we're doing in mirrors. So use the rules. A ray of light parallel to the principal axis after refraction will refract and pass through F2. This F1, F2. So after refraction, we'll have this. So we have used the first rule. You need just two rules to form an image. Okay, you can choose to use any of them. Which one do we use? Is it rule 2 or 3? Class, do we use rule 2 or 3?
Rule 2.
Okay, so rule 2 says that a ray of light from the object through the principal focus after refraction must go parallel to the principal axis. So incidence refracted. Now where the refracted rays intersect, that will be the point where the image will be formed. Frank.
Sir, please, what if you draw another ray diagram for the foot of the object? Do you still get the same size of the image?
The rays is always, you see, coming from the head. This is because the foot, the object, the image is always on the principal axis. Okay, so your two rays must always come from the head and not the foot, because the foot would always, of the object, the image will always be on the principal axis, just as we did in mirrors. And when you do that, it will just, you see, because you have so many rays, it wouldn't be nice. So we only pick maximum 2-3 rays from the head, and at the end of it, we know the foot is on the principal axis. So let's describe the nature of the image we have here. What's the nature of the image we have? 1. Yes. Frank, image is?
The image is inverted.
One image is inverted. Daisy. Okay, Yasmin. Yasmin wants to.
Image is diminished.
Image is diminished. Uh-huh. 3. Frank.
The image is virtual.
Okay, nice points. You see, in mirrors, virtual images are at the opposite side of the object. In lenses, okay, so in mirrors, virtual images are at the opposite side of the object. Real images are at the same side as the object. Please, it's direct opposite in lenses. In lenses, when the image is at the opposite side of the object, it is real. Please put that down for me. Frank.
So if you look through the lens and the object is behind, like seen behind the lens, is real.
Come again.
I said if you look through the side, like you look through the lens, like the opposite side, and you see the object like at the opposite side, like at the opposite side of the lens.
It's
So
real.
it's real. Okay.
Yes. So in ray diagram, that is how it is for lenses. In lenses, real images are at the opposite side of the object. Virtual images are at the same side as the object. So here the image is real. Image is real. It's the opposite of what we saw in mirrors. Please take note of that for me. Then image is formed between F and 2F. Jackson Echo.
Please, sorry, I was about to see it.
Okay. Image is formed between F and 2F. Please place the object at 2F. Object at 2F. At 2F. And use ray diagram to describe the nature of the image formed. Start work. Start work. I'm giving you 5 minutes to quickly do that. Object at 2F. Don't forget to take your measurements. Take your measurement, I beg you, because if you don't do that, it will affect the location of your answer. Frank, are you done?
Yes, please.
Okay, let's wait for them to also quickly finish. Then we discuss it together. Jasmine, you're also there. Janelle. Hello, Janelle. No, Janelle is not around today. So we have 2 minutes. Okay, Frank, thank you. No, so Frank, the refraction occurred at the boundary. Refraction occurred at the boundary. Look at the rays as they enter into the lens. They got bent there and then. But in refraction, we saw it, that refraction of light occurs at the boundary between the two media. So let's draw a ray of light parallel to the principal axis after refraction must pass through F, the second F. Let's vary our rule. A ray of light hitting the optical center would go undeviated. So this is where the two rays are intersecting. You see, ideally, the rays must actually meet at 2F. But because I am not taking into consideration measurement of my focal length, radius of curvature, and all that, that is why there is that slight shift. Frank. Hello, Frank.
Yes, sir.
Your hand is up.
Oh, sir, please, sorry, mistake.
Gideon.
So, but equally, when the ray passes through the first focal point, you will still get the image formed at 2F.
Exactly. I only varied the rules, okay? But equally, okay, if I could have considered a ray passing through F, and after refraction, the refracted ray is expected to travel parallel to the principal axis. All that I'm saying is that when you are doing this, take your measurement very, very well. Else it will affect the accuracy of your work. Saki. Hello, Saki.
What if you use the first row and the second row instead of the first and the third row?
You can use any two. You can use any two. So let's look at the nature of the image. Describe the image form. One, images. Hello, images. Gideon, images.
So this image is formed at 2F.
So formed at 2F. Two. Angie.
The image is real.
Image is
Real.
image is real. All real images must be inverted. Okay. All real images are inverted. Yasmin.
The image size equals to the object size.
So image size is the same as object size. I think, Michelle.
The image is formed on the other side of the lens.
That is why, Michelle, the image is real. Okay.
Okay. Yes, please.
So your assignment is that place object at one between optical center and F. And two, place object at F. The first one is between C, please, this is C and F. Two, at C, at F. And the third one is that at infinity. And then you use ray diagram to describe the nature of image form. Between C and F, optical center and F. Don't be confused with center of curvature. This time, for lenses, it is 2F. So optical center and F, and 2 at F, and 3 at infinity. Okay? And then in each case, describe the nature of the image formed. Describe the nature of the image formed. Frank, what's the question?
I have a question. I got the object height to be equal to the image height, but the image wasn't formed at 2F. Is that a problem?
That is a problem. When you place the object at 2F, it's a must that image must be formed at the other 2F. If it doesn't form at 2F, then it means maybe your measurements were not accurate. Your focal length, okay, must be equal to the distance between F and 2F. So this measurement must be looked at. Ensure that the ray coming from the object is truly parallel to the principal axis and all that. Are you okay?
Say, but my image height was equal to the object height. So does that like
that can happen by coincidence, but it must be formed at 2F once it is at 2F. So when I'm marking, even the position of the image is what I'll consider, look at. Okay. So just find time, probe it again, and then you definitely see where perhaps you went wrong. And whenever you are doing this, please, it's advisable you use well-sharpened pencil. The reason is that you may be wrong in one or two, and with a pencil, you can always erase and then correct. If you use pen, correction, the word ray diagram must be neat. Must be neat. So when you have a lot of cancellations or correct, it doesn't make it nice. So use pencil for this, well-sharpened pencil, and let your lines be clearer. Gideon.
So please, for the assignment, the first one, when you say you place the object between the optical center and F, so is it near F or near C, or exactly in between?
Between, whether it's near or at the center or close to F, it's still between. Don't forget, okay, it's the same as what we saw for mirrors. Okay.
Okay, so but the optical center is the C in the diagram, right?
The optical center is the center of the lens.
Okay, so that will be the C. Okay, thank you.
So C. All right. Class, is there any question? If there is no question, I think our time is up. Okay. I Echo.
Please, for 2, object at F doesn't mean the image will also be at F.
Echo, your question is similar to me giving you a question and then also providing you with the answer. So you just use ray diagram, and you when you get it wrong, we'll discuss it. Okay. Okay. So
yes,
just do your part, and we'll see what will happen. All right. So class, this is where we end the show today. I think it's been exciting. At least our knowledge on mirrors must help in this. Okay, but I'll find time to take you through the lens formula and its application. But next week we'll continue with our heat and the other. For light, it's a bit broad, but we cannot spend all the time on light, so we'll continue. Okay, so may the good Lord be with you. Take care of yourselves, and bye-bye.
Bye.
Bye.